the bar magnet and related topics regarding magnetism. Now this chapter has been divided into several units, or sorry, several lessons, and we have to discuss this entire chapter into many teaching points. In the first set of teaching points, in lesson 1, there are 3 main teaching topics: bar magnet, magnetic field intensity of a bar magnet at axial position, and magnetic field intensity of bar magnet at equatorial position. You will recall that in the unit or chapter of electrostatics, we discussed electric dipole, and in the electric dipole we also discussed the electric field intensity of electric dipole at these 2 positions, that is axial position and equatorial position. The same thing is being done in the magnetism chapter, and I will not be surprised if you look at the equations. You will find quite similarity between what we derived in the electrostatics chapter and what we are going to attempt in this lesson. After this lesson, you will be in a position to understand and visualize a bar magnet, its magnetic field around it, and you will also be able to understand the relationship for the magnetic field intensity, how it is derived, what is the pictorial representation, and what is the relationship between the magnetic field intensities in these 2 positions. So let us see what a bar magnet is and how it looks like. In your screen now, you see on the right there is a bar magnet. The bar magnet has a north pole and a south pole, and there are several lines drawn between these 2 outside the magnet. And you also notice that these lines which are drawn on this diagram, they are called magnetic field lines. They are called magnetic field lines. And I would like to recall, the magnetic field lines are similar to electric field lines, but along the magnetic field lines, a magnetic force is experienced by a north pole of a very small magnet. Small magnets, which are in the form of needles, are called magnetic compass. Magnetic compass is a magnetic detector. What is the meaning of this? The meaning of this is that if there is a slight fluctuation or slight movement of the magnetic compass in a given position in space, then we are sure that at that position there is a presence of magnetic field. Because in magnetic field only magnets experience a force. So magnetic compass is also called a magnetic detector. And you know, in a magnet there are 2 poles. So these field lines are nothing but curves in space. Anywhere. Space can be anywhere. This is also space. Space does not necessarily mean that it has to be vacuum. Space is everywhere. So in space, if we keep a magnetic compass and there is a magnetic field, there will be a force on the magnetic north pole, and the north pole will start moving along a certain curve. That curve is called magnetic field lines. And I want you to recall the definition of electric field lines exactly in the same way as we are defining magnetic field lines. They are similar. Now in this particular diagram, you see there are large number of field lines which seem to start from the North Pole and end up at the South Pole. How many lines are possible? Infinite lines are possible. These lines have a direction, and the direction is, as already mentioned, from the north towards the south. The rod over here is called a bar magnet. So this is magnetic field of a bar magnet, right? Now this is a figurative diagram of or representation of a magnetic field. On the left hand side, you see over here, it is an actual picture of a bar magnet which is attracting minute particles of iron, and small particles of iron distribute along the direction of the lines of the magnetic field. So you see a pattern emerging out around the space which is available in the proximity or in the vicinity of the bar magnet. Now bar magnets are pretty powerful, and I will tell you something very interesting, that if we take a bar magnet, there are points inside which are called as poles, right? We all know that. Poles means those points where there is maximum attraction. And if we take a bar magnet, these poles are a little inside from the surfaces. So the actual length of the bar magnet, if it is denoted by capital L, and the distance between the poles, if it is represented by small l, they are different. The actual length of the bar magnet will be always more. Distance between poles is always less than the actual length of a bar magnet. Now this is extremely important for you to understand. Also, there must be some question coming in your mind that how do we know the exact position of the poles? And we do a small activity. And the activity is that if we take a bar magnet and keep it on a piece of paper, and then we bring a compass close to it, the compass will be aligned in this way, at this position. If we keep it over here, it will be aligned in this way, and if we keep over here, it will align in this way. So we get three clear directions along which, if we draw a straight line, they seem to meet somewhere here. Now this point is the pole of the bar magnet. Now we quite often do all these activities in the lower classes, for example in grade 7th or 8th. But if we ask anybody how to find out the exact location, tell us with the help of an activity, it becomes really difficult for us to just recall. So for your knowledge, This is how we find out the position of the bar magnet. And it can be done on the other end of the bar magnet also. The line joining the two poles is called the axis. This line is called the axis of the bar magnet. And along the axis, if we move away, the magnetic field intensity will keep on decreasing, because as we move away, there will be decrease in the power of attraction, and therefore the magnetic field intensity will decrease. Now I would like you to understand and recall the equations for the electric dipole. Now magnets can also be treated to be as dipoles because it has two poles. Di means two, so it has two poles, north and south. Electric poles, if you recall, was a positive charge and a negative charge kept at a distance. And you will also recall that we talked about the dipole moment P, and that was equal to, or that is equal to Q, that is charge on each, into 2L, the distance between the two charges. This is called the dipole moment, and the direction of the dipole moment, it is a vector quantity, was along the direction of the length between the two charges from negative to positive. And here, for your information, I tell you, the negative pole is the south pole, and positive pole is north. This is just a convention. It has nothing to do with the values of positive or negatives, but just to give a sign and to compare the electric dipole with magnetic dipole. So this is about the bar magnet. A bar magnet is a simple rod which has been magnetized strongly by any magnetic field, and there are points inside the bar magnet which are called poles. How to find out the poles? I have told you the activity, and I have also shown you the figure or the figurative representation of the magnetic field, which is on the right of the screen in this diagram. And on the left hand screen, it is the actual picture of the alignment of small particles of iron spread over a bar magnet. And you can very well see that there is a pattern which emerges out.